Thanks. Hi. This is going to be a talk that sort of, I was realizing as I sat there, is really something about why I really like working in California, because it always manages to surprise and engage. I'm mostly, in recent years, probably, well, I've certainly been focusing more on large storms and their consequences. But currently, California is still in a big drought. Certainly, for the past year, we've been dealing with a major drought. Got the U.S. Drought Monitor there, which we've been looking at all year long, watching the red blob wax and wane, but only wane a little bit. And actually, the storms that we've had in the last week or so are really not that big a deal in terms of filling in the gap that we've had, especially if you look over just the past few years. So it has been impossible to work in California without thinking about droughts for the last year. But first, I want to talk with you about large storms, and you'll see why in a minute. California, it really is a special place in terms of its hydroclimatology within the U.S. Here we're looking at the coefficient of variations of water year total precipitation at co-op stations all around the country. And you see the green, blue, black area there that is California. And that's areas that have standard deviations that are half to three-quarters the long-term means there. The rest of the country is down in the anywhere from 10% to maybe creeping up on 30%. So really, truly, California sticks out as a place that has a really remarkably variable climate, precipitation climate. And just before we dive into the drought, I'd just like to note that we really do get very large storms here. Now, it might not take too much to convince you guys if you were walking around trying to find a restaurant last night, but we really do get big storms. On this slide, the red and yellow dots are co-op stations where their largest historical 3-day total of precipitation was greater than 400 millimeters of water. That's all of them for the U.S. for stations with more than 30 years of record. And you can see that the yellow and red dots all live either in California, in our various mountains, or in the southeast, sort of the hurricane belt, the southeast part of the country. So really our very largest storms are every bit as big by this measure as landfalling hurricanes and the like. So we get big storms, bear that in mind. So let's turn to the drought. How are droughts made? This time series is essentially the total water precipitation, water year precipitation for that red, big old Central Valley sort of catchment up there. The histogram is the annual values, the water year values. The black curve is a 5-year moving average through it. And the arrows are me just kind of going along and pointing to the major droughts historically on the basis of the 5-year moving average there. How are droughts made? I went into this looking and thinking that droughts in California, some of the really nasty ones, are multi-year events. And it seemed to me that our largest storms were pretty much random shots out of heaven or hell or wherever. And so that drought kind of had to come from the rest of the distribution, from the not really big, shoddy sort of major storms. I found quite the opposite. If you look here, so we've got the same figure up above, and here what we're looking at is just the number of wet days that fall into a long-term 95th percentile and greater precipitation total. So this is number of wet days. The red one is the large number of large storms by that measure, and the green curve back there is the 95th percentile. And actually, if we just count the number of wet days, well, a number of wet days, it's over here is the black curve. Not surprisingly, the black curve and the green curve follow each other because 95% of the wet days are in the green bin. But if you look, the red curve is going on quite swimmingly and following, is doing its thing. It's a very similar thing, but it's doing its thing. And if you compare that, and I've moved the same arrows from up there to down there. If you compare where the big droughts are, okay, the big droughts actually are following the number of these big wet days. And that's all good and well, and that was sort of like, oh, that's interesting. But if you take a slightly different look at it and ask just sort of how much of the total precipitation is contributed by those two bins, the 95th percentile storms and the rest, you get this curve. We've got the same total curve up on top there. About 2/3 of the total is in the green bin on average, which is the smaller storms. And the red curve is the 95th percentile and greater storms. And about a third is left over that shows up in those largest storms. And I invite you to sort of look at some of, not just the ups and downs, and now the vertical lines here replace the arrows in the previous diagram, but actually look at some of the little ticks on the top of these big swings. These things are following each other really remarkably closely. It was a shock. And the green curves have got some elements of the same sorts of things going on, but they're not really following very well at all. And if you don't like wiggle matching, here we go with an XY version of that. The dark red dots here are that 5-year moving average, what we were looking at up here. That's the 5-year moving average. The orange dots in the background are the unfiltered version of that, and same sort of thing going on with the green. The dark green is the 5-year moving average. The lighter one is the unfiltered. And and basically, you can see the punchline there is that 92% of the variance of the 5-year on a multi-year, sort of 5-year level, is explained by the 95th percentile storm days. And even if we don't filter it, if that upsets you a little bit on an annual basis, 85%. Those are remarkably high percentages captured. I don't know, I can't come up with another way to capture that much variance with something kind of this sort of statistic. And the other wet days are way down, way down. But I will say, before you run off to look for this in your backyard, this is a California thing. This is a California thing. Here I'm looking at a slightly different version of the statistic, but this is still basically the contributions from the top on average over lots of years, 7 days. So take all the days, take enough to get 7 per year, and then count, and then, anyway, top 7 days. And basically, that's a way of equalizing the fact that they get a lot more wet days over here. And so 95th percentile, kind of lots more storms go into that bin. But anyway, you can see here that the variance is captured by that top little tier of major storms is really, this is where it happens. Can't give a talk these days without sort of saying, I guess I should say, I'll phrase this, we know what the storms are that are doing this, or at least we know the major contributor. Our big storms really are atmospheric river storms of the sort that has been pummeling us off and on for the last couple of days. And this thing up here, in case you don't know, those colors are total vapor in the atmosphere, and this is about 2 weeks worth of imagery being animated. But here we're counting the number of landfalls of a particular kind of atmospheric river, which is a Pineapple Express storm, which is one that I know how to count all the way back for the past 60 years. The more generic version of atmospheric rivers, we haven't quite gotten to the point where we can actually call out exactly how many have happened way back before much of the satellite era. But basically, same sort of thing. The numbers are the actual raw numbers are the histograms. The orange curve here is the 5-year moving average. And by the way, if you want to know a lot more about these critters, come to the session 833Q this afternoon. We're going to be talking all about these things. And not surprisingly, if I take that curve and bring it up and lay it on the black curve that we've been looking at again and again in this talk, there's a really nice relationship. And at least on the multi-year time scale, 75% of the variance in the total precipitation in the Central Valley, basically, Central Valley drainage is explainable in a regression sense from the numbers of this particular kind of atmospheric river arrivals in California each year. And so our droughts come about, our droughts really in California are mostly due to missing very large storms. It may seem a little bit obvious on the face of it, but I can tell you it's not obvious. We get a fair number of storms, and you would think that it would be a more holistic drought sort of thing, but ours really come off of that. It's the missing of the very largest storms. Beyond that, those missing storms, basically missing atmospheric rivers, contribute disproportionately to the formation of these multi-year droughts. Like I say, 75% is capturable by just knowing the numbers of these things. And that's despite the fact that atmospheric rivers only on long-term average constitute about 6% of the days in California. So they're way out of proportion for the number of them that you see. And as I showed with that map, I would argue that this is a very California thing. Now the question that's still on the table, and I can tell you I don't have an answer, and it's a hot topic, jump on it guys, is what causes those multi-year fluctuations in the numbers and qualities of ARs, and is that kind of variability predictable in some way from SSTs or whatever your favorite predictor is? So thanks. I'm going to burn through all my time.
Impressive timing, again, for the first 3 talks. The speakers were great. But any question? No, we still have time for questions.
Sure.
Atmospheric rivers have been identified in other parts of the world, not necessarily in the U.S. Do you expect a similar kind of situation?
I do. I'm not sure that, so atmospheric rivers primarily live over ocean basins. They get torn to bits when they come onto the land into topography. They get torn to bits pretty quickly. So, and they tend to arrive from the west. The storms march from west to east, and so they're arriving that way. And so west coasts of mid-latitude continents all around the world are affected by these critters. And I'm not sure they'll be everywhere, but I do think that in some places, like I'm betting, and I don't know if Sebastian's in the room, but I was pushing him to have a look at this sort of thing in Chile. Maybe in parts of Europe, although there's so many other kinds of storm mechanisms going on big storm mechanisms going on in Europe that I'm not sure that it'll work. But I think I don't see any reason why it couldn't happen elsewhere. On the other hand, if you noticed that map, it really was a California thing. I didn't say it was a West Coast thing. I think it's a combination of being a relatively dry place compared to, say, the Pacific Northwest, and having this, really a single primary way of making big storms.
Wait, we have one more question.
Okay. Hey.
Hi.
On average, it's multiple storms. I think the question is, kind of how do you make the wet periods in some sense? And in California, on average, I would say it's almost certainly multiple storms. there are occasions, and kind of not anecdotal sounds derogatory, but there are occasions that you can look at it in the historical record where kind of it was one big storm sequence that did the whole work. But typically, you know, it is multiple storms, and in some ways that's why the count of large storms is was a decent predictor for the totals. The actual contributions from the big storms is a exquisite explainer of the of the year-to-year totals.